There you go.
All right. Good. So I hope to post video lectures every day. You remember this from E&M, except it was already done for you. This time we're recording live. So before I begin, I want to talk about the course and perhaps about our graduate program very quickly in Relativity as well, which starts this fall. We expect GTA positions next year, but I'm going to record all lectures, and I already have lecture notes. It'll be posted on the course website. You should already find the link in Canvas, correct? We'll go through everything in great detail. Yeah, I think that's okay. Okay, so before I begin, the context of how to learn relativity at different stages. You could be a physics major with an interest in relativity. Interest can eventually become an obsession, and for some of us, it becomes a fetish. So I'm going to explain all of that in terms of choices and how to go on learning. So we'll start at the very beginning. So so this is where do you begin? Well, one place you can begin is Relativity 1 right here at Troy, and even 2, but that you already know. So at the same time you're thinking, well, good, I know how to wheel through the calculus of relativity. I understand black holes, I understand cosmology, the nature of space and time, but I want to do more. But I'm a physicist. I don't want to get into all the math theorem, but I just want to continuously progress. There's a great choice. There's a second book, well, these come with notes as well. There's a book called The Relativist Toolkit. I don't know. Toolkit by Eric I haven't read the book, but what I have done is watched his set of videos at Perimeter Institute. So after this course, this video course, it's just one semester long, it's excellent. And you can read along with this book that he has written. Okay, you learn a lot more about GR, and it's literally no more effort. You already know all the things you need to get started with that course. There's a third set of notes by Matthias Blau. It's about 1,000 pages. You can pick and choose what you want if you find something interesting there. Okay? So, in my opinion, with the math of tensor calculus, you can learn a good bit. I would at least recommend Eric's course, and maybe you can download this one and keep this. I think it's very useful. Okay, so this is all the physics. You know GR very well. You know gravity very well, but it's not the math, pure math theorems. There's a second here. Oh, so all of this is general relativity. And in my opinion, for the longest time, I couldn't find a good book in special relativity. And special relativity, I'm truly inspired by this book. There are a few books written to actually teach, right? This is one of those great books. It requires nothing more than what we have here, maybe a little bit more linear algebra. This is a book on special relativity called The Geometry Minkowski spacetime. This is by Gregory It's meant for mathematicians, but it's not difficult math. You know, it's linear algebra, just matrices. And you'll also learn to use linear algebra very well. So this is on the side. You will see very quickly that this is special relativity. Okay. So then there is the next category. You've had this and you're going, well, I've been learning math as well, I don't want to stop now. And somehow you've taken a year of real analysis and you're feeling pretty good, strong about real analysis. There are 3 books. I'll write my favorite first. The first one is called The Geometry, Semi-Riemannian. I don't know how many M's in semi-Riemannian geometry with applications to so for this, everything in this category you'll need to know: analysis and topology. Fairly standard analysis and topology, but this will prove everything, every jot and tittle of the mathematical aspects of relativity. And then there is all the theorems you need put together in one place in an almost impenetrable book called A Large-Scale Structure of Space-Time. Oh, this book is by Barrett O'Neill. This is by Hawking and Ellis. This should do it, but there's a good third one in this category, and it's called globally Lorentzian geometry. Beam and Ehrlich. I don't know how to spell Ehrlich, so I'll write B and E. So this is the second category. So but then you've had all of this, and end of the day, in physics, just like Maxwell's equations that you have seen, general relativity has a partial differential equation. It's a nonlinear partial differential equation. And if you want to study the properties of Einstein's field equation, this is the nonlinear PDE, there's a book called The Cauchy Problem in General Relativity, or Relativity, I can't remember. So it's relativity. By Hans Ringstrom. So these are the 3 stages of general relativity. This is on the side. This, after my first 2 chapters, if you're good with linear algebra, you can start reading. It's a great book. And we've been in fact, my first 2 chapters are almost entirely inspired by this book. This is tensor calculus. This is all the mathematical theorems about space and time. When you have time machines, when you have warp drives, or when do you not have them? If you do have them, what are the problems with space and time? You know, causality becomes a big thing. All this, the nature of space and time, you don't take it for granted. We're solving for all of this, right? So this happens all of that, and this is purely partial differential equations. So this is the, if you will, one catalog of general relativity in its entirety, soup to nuts, if you will. This is exactly what we do in the graduate program. You will go through, or should I say, you will endure 3 years of 3 sequences of general relativity. You'll start here, and that's what we're doing. You'll take 1 year of this. Should you choose to, you'll take this. Okay? So that is the nature of general relativity, mathematical relativity, and our program here, our graduate program here. Now I'll give you a quick rundown of what we will do in our course, both this semester and next semester. Any questions so far? Okay, so now, I tend to be very slow in covering material. I go through things in great detail. If I make a mistake, please let me know, either while I'm giving a lecture or perhaps if you notice something. And this is especially true of my lecture notes. Check both the math content and language as well. I continuously edit it and update it. So at the moment I have 2 short chapters, the first 2 introductory chapters in there, and as we cover the other chapters, I'll add more and more. The way to study is, of course, you pay attention in class, and then you'll be assigned problems. They're already in the notes. They're built into the lecture notes. Tackle those homework problems. If you have any questions with me, for me, so before we begin the next day, your job would be to ask me questions about the previous lecture. Don't let anything slide. So I'll start with any questions that you might have. Once I have cleared that, then I'll move on with the lecture. Okay? And I say this all the time. I'd like to start at the very beginning. You might know a little bit of special relativity. You might have seen Lorentz transformation, maybe. Show of hands, how many of you have seen Lorentz? Yeah, that's not required. If you have seen it, great. It'll only help, right? You'll have more intuition with it. That's literally where I'll start. But we'll move very rapidly, okay? This is an interesting course. I have about 9-10 people here. I have 3 online. I have undergraduate students. I have graduate students. I might even have a sophomore in here. And that has traditionally been the case. Sophomores have done well. Okay, so there's, like I said, we'll do everything right from the beginning. So let's start at the very beginning. I don't know how Einstein deduced that speed of light is a constant. We'll talk about exactly what that means. It was not based on an experimental analysis. Perhaps historians of relativity might know this, but the whole formulation of special relativity and general relativity was very unusual. He tackled the problem and wrote the complete set of equations, right? Just all of it. And then people added to it and clarified it, cleaned up the math. A lot of effort has been done. We understand relativity a lot more than Einstein ever did, but that's 100 years after, right? So if you have taken electrodynamics, you saw Coulomb's law, you saw Biot-Savat's law, you saw Faraday's law of induction, and somehow we hodgepodged it together and we said Maxwell's equations. No, there are no components of it. It is just general relativity, right? And we haven't modified that equation in 100 years. People have tried. People are still trying. There seems to be no clear advantage. So what I'll do is I'll talk about special relativity. talk about everything in detail in terms of time dilation, the twin paradox that you may have seen, but I'll draw diagrams for all of that. Okay? And then we'll slowly move on to what happens to space and time if there is gravity. Turns out it's not like another electric field or magnetic field. It is changing the very nature of space and time. And so we'll do a little bit of tensor calculus, just what we need, math as needed. And then we'll analyze one solution. There are many ways to understand the theory. You can study, write the equations down, study the properties of equations, and then do some homework problems. That's not what we'll do. We will describe a non-rotating black hole. We'll intuit the solution, we'll intuit the answer, and then we'll spend a month on analyzing what that answer means. What does that space-time mean? In doing so, we'll understand all about the properties of a black hole. We'll talk about entirely mathematically things like event horizon, the singularity, and extending space-time, maybe a white hole, all of that together. So we'll analyze so that we have an intuitive understanding what general relativity does. And then, as the next semester begins, we'll do a little more math as needed to derive the full Einstein equation. Having done so, the second half of next semester will be devoted to a class of spacetimes that describe our universe. And typically, this is called cosmology. This field is called cosmology, but we're going to focus about the nature of space and time in cosmology. What precisely does Big Bang mean? Maybe what could be inflation, why we may need it. But again, I'm not focusing on what's called physical cosmology. What are the particles, when were they created, what's the temperature, when did galaxy form? That's different. This is, of course, in general relativity. What does space and time look like when you have galaxies peppered in the universe? Okay? That's the length and breadth of this course. Okay, so if you will, special relativity, we need two axioms to start with. One of them is speed of light. C stands for speed of light. Is a constant for all inertial observers. And I'll talk a little bit more, and I'll talk initially a little bit more about inertial observers, and then we'll talk a lot more about inertial observers. More on this, more on both. And the laws of physics are valid for all. I'm not being very precise, so let me look at how laws of physics take the same form in all inertial take the same form in all inertial, I'm not being so rigid, frames. So when you look at these two sentences, it doesn't look like it's saying much. Secondly, it's not saying anything at all, because we really have been talking about what's true for inertial observers, not telling you what who inertial observers are. So this, I could say anything about this. But, if you will, what physical law do we worry about now? What physical law do we start with today? Let's start with F equals ma. Okay? Newton's first law, for example, says if you have a free object, an object that is not being acted upon by a force, what will it do? An object will either be at rest. If it is initially at rest, it'll stay at rest. But if it's moving, how will it move?
With no acceleration.
Correct, with no acceleration. Velocity is a constant. velocity is a constant means two different things. The speed is a constant and the direction of motion is a constant. So for us, that's good enough. That's the physical law we'll work with. And so in particular, if you have an inertial observer using those set of laws, and the inertial observer is looking at a free particle, nothing is acting on it, can the inertial observer be accelerating? No way, because then the free particle will look like it's accelerating, right? So in some sense, the most an inertial observer can do is what? Move with a constant velocity. Otherwise, another free object will not have a constant velocity. It could do other things. It could be rotated. You could choose to observe the particle upside down or rotate it sideways. Or you could choose to observe the particle in Troy, Alabama or in New York City. So there are some choices there. You can use a different clock. You can measure time in seconds, minutes, or Central Standard Time or Eastern Standard Time. All of that is allowed. Literally, we'll classify these, and these are the inertial observers. Okay? So we'll talk a lot more about that. So for all inertial observers, speed of light is a constant. It turns out light just happens to have a speed that has got to do with the invariant speed of the universe. Gravity does as well. But we started out with light because back in the day, light was something you could detect and measure properly. Right? Nobody knew what gravitational waves back then. Right? So why would I even bring it in this context? We said something. We said, at most, an inertial, well, outside of rotation and going to a different location, at most an observer can do is move with a constant speed. It doesn't sound very complicated until you literally place it in context. Suppose you are standing here and you're watching something move with a speed v. On the other hand, another person gets into a car and is also moving with a different speed, let's call this u. So here's a particle moving with speed u according to this guy, inertial observer, okay? And this car is moving with a speed v. What will this car measure the speed of this object to be?
V minus u.
V minus u. Or sorry, u minus v.
Yeah, because objects for
Yeah, u minus. It makes sense. If you throw something at 30 miles per hour, and if a car is moving that in the same direction at 20 miles per hour, somebody in the car will watch at 10 miles per hour. Not true if this is replaced with a photon torpedo. It's a beam of light. It's a pulse of light. This person, now you might say, well, that's kind of pointless. Car is traveling at 30 miles per hour. Light travels at 300 million meters per second. So it's roughly gosh, that's like saying the distance to Montgomery is not 42 miles, but 42 miles in 1/10 of an inch. Come on. There's no physics in there. It's not true. Suppose this is instead a spaceship or a comet that's traveling at half the speed of light. That comet would view the same beam of light, not at half the speed, not the remaining half the speed of light, but the full exact speed of light. I mean, Einstein just spunk it up, really. There's no explanation for it. Years later, I think people verified it, and he was not even aware of the result. He spoke directly to the universe. It's just not even, somebody verified his claim, right? All right. So that is just unusual. The only way you can have this wild card that is the speed of light. Speed is what? Distance over time. So if this guy is moving, distance is changing, the moving observer's time has to change so that when the moving observer measures his or her distance and time taken and takes the ratio, it changes in such a way that this only when it's speed of light, it just cancels and it becomes all the extra things cancel and then you get C again. The same number C. So easy, we will see this is easy to handle mathematically. We'll draw Minkowski diagrams as they're called. There's a way to intuit this after a while. But that is not necessarily physics. This is pure philosophy, that such a thing should exist. So we'll begin by exactly studying how relative, if you have two observers, how are their space and time related? And that's the difficult part of special relativity. Then we'll talk a little bit more about rotation and translation, meaning doing physics from New York, or even time translation using Eastern Standard Time, and all of that, and put it together for a nice mathematical picture. But that which we cannot prove is the most profound statement in science, because everything is stacked on these two statements. You want to get a Nobel Prize? Disprove one of these. Easy as that. Have people been trying? Oh yeah. Are people trying now? Oh yeah. If that happens, we just have to learn to deal with reality in a different way. Something has to break in mathematics and physics. Something will have to break in philosophy. At this moment you're going, well, this is convoluted, I don't know how I'm going to unpack it. It turns out it's going to be linear equation. It's not even quadratic. An 8th grader, you give me a month with an 8th grader, they'll know special relativity. Yeah, it's not complicated. Philosophically, it is. We'll unpack this. Okay? All right, yeah, good. Any questions? Oh, I should have done this. I should have retained my fine art there. How do I draw a spaceship, David?
That's not it.
You got it?
Right over the top.
It's a slingshot.
For this class, that's a spaceship.
Okay.
It's moving with speed. So you have two observers. And we're going to keep things one dimension, not a good spaceship.
It's more futuristic.
If you watch the old Flash Gordon movies, like the
Yeah,
old
yes.
Flash Gordon,
Yes, okay.
Are
Yeah.
we supposed to be serious on
For sure.
recording?
This is true. This is true.
okay, so this guy, we'll call this person the stationary observer and moving observer. That's, no pun intended, relative. So this guy is going to use t for time and x for space. I don't want to use the same symbol. I'll use t bar and x bar for the moving observer. Some books use primes, some use tildes. Other books say Bob and Alice and have B and A subscripts. They're all equivalent, but I'm a creature of habit. This is the one I'm fond of. So suppose special relativity is not what we're concerned with. Tell me what's on the right-hand side.
It's the tool.
So if you're, oh, good. I'm not even clarifying what it means on the right-hand side. Suppose, and once I draw this diagram, it'll be very clear. Suppose I have an object here. And then I'm measuring the distance, x. this moving observer measures a distance, x bar. This distance, now you know the answer already, is, let's assume that at t equal to 0, when the experiment started, this moving observer was right here. So in t seconds, this spaceship or rocket ship has moved a distance, at, distance times time. This is what it would be if we are not studying relativity. If you, a couple of years ago when you were doing freshman physics, that's what it was. I know I can't use this because speed of light just won't be a constant. We've done Newtonian physics before, if you will. So we need to find a way to modify it so that the speed of light is a constant. Sorry? Yeah, right. So we're going to use a trick. And the trick works only because it works. What I'm going to do might look like a proof. It is not a proof. This bothered me for the longest time till I read the book by Gregory Neighbor. So I give you what's called a heuristic proof, this argument, so that just we can sleep better at night. It has no other deeper meaning. So you multiply by a factor because the simplest explanation is probably the correct one. And that is true. Very often it is the simplest explanation. But I said very often. If Einstein does it, he'll get away with it. If you and I do it, we'll crash and burn. So we don't have this luxury, but people with insight do. So I'm not sure if it was Einstein who did it, or Lorentz, or Minkowski. I'm not very good with the history. I really should be a little more careful, but I invite you to read up on the history of relativity. So there's a factor here, so I'm just going to give a little space. And it's a gamma. This gamma is supposed to be a constant because we're looking for the simplest explanation. Mind you, it's not a proof. I want something that works. And then we'll do problems. And then we'll talk about why it works. This gamma is a constant. But what could gamma depend on? Obviously, it has to depend on C. Gamma should be a function of C. And gamma should, what are the parameters that's there? V. So gamma can only depend on V. And then, so gamma's a constant, right? It doesn't, you pick C, you pick V, and gamma's a number, it'll be 7. It cannot be 1/2. Let's see. Okay, let's use intuition. Suppose I change the role of who's moving and who's not moving. I'm going to write an equation, tell me if that makes sense. After all, we're just intuiting. And compare it to that. I pause, so you can go, If I change the role of who is moving and who is not moving, what am I doing? Changing V to minus V. Because with this guy, this observer is moving with negative V. According to spaceship, he or she is not going anywhere. No matter what time it is, you're exactly where you were in the spaceship.
And it won't be 1 over gamma in this case?
No, gamma is a constant.
Okay.
Gamma is a constant. Yeah? So all I do, I can make this bar, and then I can replace it with minus V. Is that clear, everyone? Veronica? Yeah. So according to the spaceship, the other guy's moving the other way. Okay, let me make sure my argument is clean. And so what I'm going to do is, I'm going to take, so I'm going to call this 1. I'm going to take this equation and put it in here. I take this equation, put it here. So I get x bar equals gamma x, which is actually gamma squared x bar plus v t bar minus gamma v t. Correct? So I'm going to solve this equation for t. I don't want to waste time here. Please verify, check. So some of the algebra you should check at home. Some of the calculus you'll have to check at home. It's a good check to make sure you're following the argument, and also it's a good check to make sure I'm not making a mistake. Gamma t bar minus 1 minus gamma squared over gamma v times x bar. All I did was solve for this t. You can actually see, and put these two together, I will get 1 minus gamma squared. And because I'm dividing by gamma v, I get this gamma v. That's all I've done. Now, once again, I'm going to do this trick to this trick. So you see this, so you see this transition from here to here. What did I do? Bar to no bar, and v to minus v. Right? And same thing, t bar. T, I'm going to do the same step over here. Now, to make sure you're paying attention, tell me what I'll get. I'm going to do these three things, and I want you to reconstruct this equation very quickly.
Should be,
Just read it out quickly.
so you get t bar
T bar
is equal to gamma t plus,
because of this v.
yeah, it'll just be the same thing. And just x instead of x.
Just x.
Or, wait, sorry, that t is supposed to be a regular t. The first t is supposed to be a
Oh,
regular t.
right. Sorry. Thank you.
That's my
Yeah,
bad.
yeah. This equation I'm going to call 2. I couldn't have really gained any advantage here because all I've done is just played with writing things back and forth and back and forth. There's no insight. Now I have to bring in actual physics. I'm going to look at a photon, a beam of light, a chunk of light, matter, a piece of light. I don't want to say that. But that moves at the speed of light, a photon. So that means if you look at the path traced by x equals ct, what will the spaceship see? Is that correct? Because speed of light is to be preserved. So I'm going to take this and put it in here. And when I do, so from 1, this is not, so if x equals ct, then this applies that. Then from 1, this won't be always true, but only for a beam of light. I will get ct bar equals, and I'm just making sure I don't make a mistake, it's x minus vt, so I put ct minus vt, or I get t bar equals gamma, I factor out both the t's, and I'm going to write this as the following. Is that correct? This is not always true in general. What is this true for?
Just light.
For a photon starting at the origin, at the common origin. You know this from modern physics. V over c is dimensionless, speed over speed. It's denoted by the symbol beta. So what I'm going to do, you guys will have to write it as the next line. And replace this V over C. Beta. Okay, again, I know this doesn't work all the time. Now what I'm going to do is take this and put it in here. For the moment, there's a law of conservation of space, and I've run out of space, so I'll have to erase something. Very soon we'll be able to dilate it, or contract it, or even tear it. I'm going to take this equation and put it into this one. So I would get 1 minus beta equals gamma t plus, what am I doing? 1 gamma t, 1 minus gamma squared over gamma v. And I'm going to specialize this to speed of light, photon, because at the end of the day, this is only true for a photon. Okay? Right? I replaced x with ct. Good news is what? T cancels. And so I get, well, not only t cancels, gamma t here, gamma t over here. So I would get minus, what is that, beta gamma is equal to 1 minus gamma squared, gamma v over c is beta. And I hope I haven't messed the algebra up. Is that correct, guys? Keeping track of everything? Let's just move on. If it works, it works. It was in my notes, so I'm assuming it's correct.
Yes.
Well, let's see what happens. Minus gamma squared beta squared is 1 minus gamma squared. All right, I can bring the gammas together, so then I get what? That's not right. Oh, it is right. Gamma squared times 1 minus beta squared equals 1. So I have gamma is plus or minus square root. So I have evaluated what gamma should be for a beam of light. But gamma is a constant. Right? That was the premise starting all along. So we're going to pick one of these two. So we started with x bar equals gamma times x minus vt. If I put a negative number here, does that make any sense? For the premise that we started with? No. So I am going to pick this choice of gamma. I have no other choice. I have to pick this. All right. Oh, I might need some of that. So what I'm going to do is I'm going to literally put the value of gamma in here. I will let you verify. Oh, you write it below and below in your notes. And then I box things. I'm going to take this gamma and I'm going to put it in here. Just leave this one alone. When I do, you will find T bar equals gamma T minus V or beta over c you will see this to be v over c squared x. Don't box it up. So you get this, you need to verify. So this goes into this, and this is written as that. So let me conclude. That's enough algebra for the day. Conclude the following. X bar is gamma x minus vt. And instead of t, I'm going to multiply this entire equation by c. I'll tell you why I'm doing that. It'll look nicer, but it'll have a better meaning. Ct minus beta x. Beta equals v over c. Gamma equals 1 over square root 1 minus beta squared. We'll box this. There's a lot of, it's good to be done with algebra, but there's meaning to be extracted from this. What does this mean? But I think I'm glad that time ran out because it's a good place to start. We've cleaned up the math. On Friday, we'll talk more physics.
Just push the button.